So our next speaker is Subir Sachdev from Harvard University, and he's gonna tell us about large N theories of non-Fermi liquids. So please.
Okay, well, thank you very much, Adolfo. So it's a pleasure to speak here at this conference. I've heard a lot of interesting talk from a wide variety of fields. So it's nice to have this interdisciplinary discussion. And I hope there'll be similar interdisciplinary ideas in my talk. So let me just begin by, just asking the basic question: what is a non-Fermi liquid? It means different things even in condensed matter physics to different people. If you ask experimentalists, well, they'll say there's lots of examples, sometimes called strange metals, where you have resistance as a function of temperature, having a very unusual behavior. This is common in essentially all high temperature superconductors, like the pnictides here or the cuprates, where again you have a regime of strange metal behavior. But this is going to be a purely theoretical talk. I won't say much about the experimental situation at all. So I'm just going to define a non-Fermi liquid. So this is going to be my definition for this talk, and I think it's a very general and appropriate definition. So first of all, it's a state of matter that is compressible. So what does that mean? So very generally, you have some Hamiltonian, and there's a global U1 symmetry and a conserved charge associated with that, which we call Q. And then you take your Hamiltonian and you deform it a little bit with a change with the chemical potential delta mu. You get this new Hamiltonian. And then you look at the ground state of the new Hamiltonian and measure the charge in the new Hamiltonian. And the compressibility is basically the derivative of the rate of change of charge by the chemical potential. And a system is compressible if this is not zero, at zero temperature. Everything is compressible at finite temperature. So it's really a question of, is this non-zero? So many familiar systems, in fact, are not compressible by this definition. We've heard a lot about Dirac fermions and wild fermions in two and higher dimensions. Those are not compressible because the density of states vanishes at zero energy. Any conformal field theory, by a very similar argument in dimensions d greater than 1, is also not compressible. So these are not non-Fermi liquids by this definition. The second requirement is that there are no quasi-particle excitations. So this is a much more difficult requirement. And quasi-particles are so ubiquitous that we use them without even knowing that we're using them. And quasi-particle is roughly, very broadly, you can imagine a quasi-particle is a way to describe the low-lying excitations of a many-body system with total energy E. And the energy of the many-body system is written as a simple polynomial of the set of occupied states. So you can take a exponentially large number of states, exponentially large in the size of the system, and write them in terms of a polynomial of actually some number of states that's only extensive, that just goes with the volume of the system, not the exponential of the volume. So that's what a quasi-particle is in some very general abstract sense. And in fact, they are pretty much everywhere. Luttinger liquids are sometimes talked about as examples of non-Fermi liquids. They aren't by my definition because they have quasi-particles, which are these bosons, which in fact describe the complete spectrum. Any system with an energy gap, topological quantum field theories, fractional quantum Hall states, they all have quasi-particles. So with these two restrictions, however, you can ask what are actual models that are non-Fermi liquids. Just have to satisfy these two criteria. So there's actually a fairly small list, and I'm going to talk about them. So one is the complex SYK model. We heard a little bit about the complex version yesterday from Igor, and I'm going to say a bit more. So I'll describe this model. It's a model of interacting electrons or fermions, the complex refers to the fact that there's a conserved U1 charge. The Majorana SYK model doesn't have a conserved charge. And it leads to a state which has no quasi-particle excitations. Now we are almost completely sure that's the case from both analytical and numerical studies. Another model will be the focus of the new results that I'll get to is the following. You take a Fermi liquid, which is a compressible state, but does have quasi-particles. So you have a Fermi surface of some fermions where there are occupied states inside the Fermi surface and empty states outside. And then you couple it to some massless critical boson. And so this is a problem that's been studied an enormous amount in condensed matter over the last 2 decades. This boson could be an emergent gauge field, it could be some Higgs fields, it could be some autoparameter corresponding to breaking symmetry. And all of these lead to very similar but slightly different theories. And there is a lot of evidence, but no systematic theory really of that this particular state with the critical boson, you get a Fermi surface which becomes critical. That is, there are the quasi-particles that are present in Landau's framework on this line in momentum space don't exist anymore. And you're left with a complicated critical state that has no quasi-particle description. So we have some new results, further evidence that in fact, this is a consistent example of a non-Fermi liquid, which is the second part of my talk once I'm done with the introduction. Then you can ask, how about holographically? So holographically, there are examples that satisfy the 2 criteria I mentioned. One example is the following. You take essentially Einstein-Maxwell theory, and you look for black hole solutions with a net charge. So there's some horizon radius, and you take your temperature of the Hawking temperature of the black hole to be much less than the inverse of the horizon radius. And that's the so-called extremal limit of a charged black hole. Then you get a geometry that looks like this. Very far away, so there's a negative cosmological term. So if you're in 4 space-time dimensions, will be ADS4. And near the horizon of a black hole, there's a factorization where the space-time factorizes into an ADS2 geometry and the S2 geometry, which is basically the surface of the sphere of the black hole. The horizon is a sphere. Okay. And this is basically radial distance away from the horizon. That's this particular axis. So this particular theory has been studied in various guises. It is compressible because you can just change the charge on the black hole. And there's a conserved density in the dual theory that's living on the boundary. And you can vary it to anything you want. And there are no quasi-particle excitations if you look at any spectral function of operators on the boundary. So this is a holographic representation of a non-Fermi liquid, if you wish. But it's a finite non-Fermi liquid. It's sitting on a sphere, not in infinite space. Okay. So in particular, what happens is that as I'll maybe mention a bit more later on, if you look at the low energy excitation, at low temperatures, they're dominated. There are no excitations in ADS2 because it's pure 2-dimensional gravity. But there is a boundary graviton that's the first correction to the Hawking entropy of the horizon. And okay, so this has been studied a great deal. I won't say much more about that. But this example of a non-Fermi liquid, I think it's also now extremely well understood. Before I get to that, there's one way you can get exactly this theory by starting from a quantum mechanical model with no gravity. You just take the canonical, well, depending on the dimension, if you're in 5 dimensions, you take the n equals 4, if capital D was 5, then you take the n equals 4 super Yang-Mills theory, which is the canonical example of the ADS safety correspondence. put it in a chemical potential. It's got various conserved R charges. So you just put a chemical potential on one of the R charges, and then put the whole theory on a sphere. And then you take a temperature, which is much, much smaller than a temperature determined by the chemical potential. And that gives you essentially this geometry, and that presumably is describing a non-Fermi liquid. But moreover, what we now know is that this low temperature theory of this boundary graviton is in fact just the holographic dual of the complex SYK model. So this particular holographic example is, now thoroughly understood, at least its low temperature properties, as being essentially reproducing a model that we can actually, put our fingers on and put on the computer and really understand completely. Okay, so this particular pair of non-Fermi liquids is thoroughly understood, I would say, at this point. So that leaves open, this point 2. Well, there's a fourth non-Fermi liquid I want to mention, which is essentially the same holographic theory here with just one change. You don't take a spherical black hole, you take an infinite black brane. So you just have an infinite space with a super Yang-Mills on that space. And then you apply a chemical potential. So it's just a plane with, or say, suppose your D is 4, then it's a plane, and you take super Yang-Mills theory. In this case, it's n equals 8 super Yang-Mills, and you apply a chemical potential. You get some state, which is dually described by this charged black brane, which is the complete analog of this. The only difference is that the geometry being near the horizon, ADS2 cross S2 is ADS2 cross R2. So that's an important, a small but very important and significant difference. So this is an infinite system. And now the low temperature regime is not associated with the inverse horizon radius. It's just some scale set by the charge density. Okay, so this case was studied most famously in these early papers by Faulkner et al. And Subrovich et al. And what they showed was that if you put probe fermions, an extra number of fermions, that they have a critical Fermi surface, which has some similarities to this critical Fermi surface that's appeared in point 2, but also some significant differences. The entropy is not the same. There's a k-dependent exponent here that you don't find there. And also, most importantly, the radius of the Fermi wave vector is not determined by the total charge density, it's determined by the probe charge density. And that's also, not a, that's a key feature of this point 2 that's not really reproduced here. So I won't say more about this 4, except, this just to mention it because this has been studied a great deal as an example of a critical Fermi surface. It's taught us a lot, but it's also, I think, quite clear at this point that it's not holographically dual to something like this. That's closest to experimental situation. So, so what I will present today, if I have time, is some work with Ilya Sulitz-Hauyugo and Avishkar Patel on trying to understand this better. And really present what I believe is the first clean large N theory of this kind of critical Fermi surface state, and the whole approach will very much draw upon what we've learned from the correspondence between 1 and 3. And so we're just going to take the lessons from that correspondence and try to understand non-Fermi liquid 2. All right, so that's a general introduction to what I'm going to talk about. I'm happy to have questions on this particular slide before I dive into our recent work. Okay, all right. Okay, then I'll continue. Yes.
You said that you take the derivative with respect to mu at 0 temperature, but in this example, you can't go to 0 temperature. So how do you know that they're actually in comparison?
Sorry, which example?
These extremal black holes.
You can't go to 0 temperature? What do you mean?
Well, the Schwarzian theory only allows you, or the SYK only allows you to take temperatures which are non-zero, but not very small, but non-zero. You cannot go to temperatures of order 1/n.
No, okay. So the SYK model, you can go to temperatures of order 1 over n. Absolutely, you can. Temperatures of order e to the minus n, you have problems.
Yeah.
But the Schwarzschild theory applies at temperatures of order 1 over n. So there's, I think you're referring to, if I may be mistaken, the breakdown of conformal invariance, and that happens at temperature of order 1 over n. But that's consistent. That is present both in case 1 and case 3, and described by the same theory.
So how do we know that it's incompressible? You need to take a derivative at 0 temperature.
Oh, I see. Okay, so I guess I'm taking the large N limit before I take the 0 temperature limit in defining compressibility. Okay, good point. So here, when I define the compressibility SYK model, I was talking about compressibility of the charge density in the limit where I've taken the thermodynamic limit before I take the 0 temperature limit.
Thanks.
Okay. Okay. All right. So then let me just begin by reviewing some basic properties of the SYK model. Then I'll review point 2, some properties of the critical Fermi surface, and then finally point 3 will be our more recent results. So here's the complex SYK model. So you have fermions, which have some label, alpha, which goes from 1 to n, and a random 2-point interaction between them, u alpha, beta, gamma, delta, which is chosen to have 0 mean, and some variance u squared. And the distribution doesn't much matter other than the fact that they're independent random variables. It's worth mentioning, actually, this kind of model has a long history. It appeared in, it was called the two-body random ensemble in nuclear physics way back in the 80s. They presented some numerical results, and that, but there was no analytical understanding of what's going on at that time. Okay, so just a variant of this model, not exactly this one again, was discovered by Jean Bouillet and myself in '93 when we presented the solution I'm now going to describe. Okay, so, and then here I'm going to, Q is a charge density, not the total charge, with a factor of 1 over n. Okay. So in the large n limit, you can show, for example, just by expanding in powers of u, that the Green's function, first of all, becomes fully side diagonal. So there's no alpha beta index on the Green's function. It self-averages. So even in a given sample, this will be true in the large n limit. And so the Green's function is just given by this. This is the Dyson equation where there's no bare dispersion. And the entire theory is this equation for the self-energy given by the what's now called the Mellon diagram of 2Gs. All right, so now there's some analysis you can perform of these equations and understand something analytically in a limit where your times, inverse times and temperatures are much smaller than u, and n has been taken to infinity. So in this limit, you can solve these equations, and the Green's function has the following form. This is a familiar form that you know from conformal field theories, but this just appears by the solution of these two equations. In fact, it's first found by George and Parcolet. And then this exponential factor here represents a particle hole asymmetry, that times going forward and times going backward are not the same. And that particle hole asymmetry is determined by this parameter, E, capital E. And that naturally depends on the function Q, the value of the charge density. So that kind of makes sense. If Q was 1, it means every state was occupied, then you can remove a particle, but you can't add any particles. So the Green's function is purely hole-like. Similarly, when Q is 0, the Green's function is purely particle-like. And so as you vary Q between 0 and 1, you get more particle-like or hole-like character. What's a bit more surprising is that the relationship between Q and E, which is a relationship between a high energy property and a low energy property, is universal. It has the character of an anomaly matching argument or a Luttinger theorem, and is independent of all microscopic details. So there's a formula that relates Q to E, which I haven't written down here. Anyway, Q is microscopically tuned by mu and can be smoothly varied, and that's in that definition, the state is compressible. Okay, so now we can look at, now we understand a great deal about the fluctuations of the state. Before I get to that, you can write in Fourier space, you can rewrite the solution in terms of the self-energy, which has this form. It has some strange power of temperature. And then at finite temperature, it's a scaling function of the frequency divided by temperature. And this is a very it may seem kind of obvious to particle theorists who's living in the world of conformal field theories. But to a condensed matter theory, this is quite an interesting and unusual observation in this context. Because if you take a Fermi liquid, this is not true. A Fermi liquid is a gapless system with some linearly dispersing excitations. But the damping of those excitations at finite temperature is determined by some microscopic energy scale. And it goes at some high power of temperature, like T squared. Here, you have the remarkable feature that the damping of your excitations is independent of the strength of the interactions. The U doesn't appear inside the scaling function phi that determines the characteristic frequency scale of damping at finite temperature. And so that's an immediate indication that whatever particle you're looking at here doesn't really exist. It's not a well-defined state. And it's not a quasi-particle excitations the way an electron is near a Fermi surface. So this is an evidence that at least the C particle is not a quasi-particle. It doesn't mean that there could be some other particle. There could be some fractionalized degree of freedom, which is well defined, and this is some convolution of that. So that we can't rule out by this particular, but this is really the first indication that there are no quasi-particles here. All right, so we want to look a bit more at fluctuations about this large n saddle point. And that's done by what's called the G sigma theory. So let me just outline the basic steps. First, you introduce replicas, but then you ignore them because you assume that the theory self-averages, which we know quite accurately from numerical studies today. So you average over U, and you get to C to the fourth term. And then you insert this trivial identity between G and sigma, where sigma imposes the delta function that G is just the Fermion-Green's function. Then you change a few variables and you integrate out C's, and you get an exact representation with no approximation so far, other than the neglect of the replica indices for the average partition function. So the average partition function is given by this path integral of two bilocal fields, G and sigma, and this is the action, the famous G sigma action. So if you look at the saddle point of this action is, of course, the equations I've already presented, and you can solve them in the low energy limit, like I just described. So here there's a key observation by Kitev that if you look at the low energy limit, where you ignore this time derivative term, and also the chemical potential because it cancels against the zero frequency component of self energy. So if you just ignore this term here, then the remaining action has a time reparameterization symmetry, where you reparameterize time from tau to sigma and also reformulate the Green's function. Sorry, there should be tildes here because these are different Green's function in the new frame by these powers of F. There's also an emergent gauge symmetry for the complex SYK model, but let me not dwell on that. Okay, so because of this time reparameterization symmetry of the action where you throw out this term, you can argue, or at least Kitev argued, that if you want to understand the low energy properties of this theory, then you can just replace the integral over G and sigma over these two bilocal fields along a special path in this high dimensional space, which is just the reparameterization of the Green's function about the saddle point solution. Yeah, I guess I've said that here. So you take the saddle point solution and all you do is you time reparameterize it. And then instead of integrating over all G, you only integrate over f of tau. And there's a similar argument for the phase of the Green's function. That's the gauge transformation. So you take this very big integral and you reduce it to a much smaller integral over a smaller degrees of freedom, the time reparameterization and the phase phi. And then you can try to deduce this effective action either by explicit calculations in certain limits or by general symmetry arguments of this, which rely on the structure of the saddle point solution, which itself has a conformal invariance. And that's that structure of the conformal solution, which is SL2R invariant, then constrains the structure of the effective action. Okay, so this is the way, very quick summary there, how you obtain these short chain effective action with a factor of n out front. There's a short chain is in terms of this time realization field phi, f, sorry, and the U1 gauge transformation is associated with charge fluctuation, and that has a corresponding phase field phi. And there's various coupling constants. There's only two independent coupling constants here. There's the K, which is the compressibility. It turns out to be just dq d mu. And gamma is ds dt, is the temperature derivative of the entropy. All right, so this has been studied a great deal. And as I claimed earlier, the properties of this particular theory precisely match, in fact, quantitatively match the properties of this charged black hole, extremal charged black hole solution of Einstein-Maxwell theory. You can find a complete correspondence of this theory and the theory you get by looking at graviton fluctuations about that charged black hole background. Okay. And I should also mention one other important observation, which was made by Bagretz et al. Early on, was that if you now look at these f of tau fluctuations at low temperatures and look at their consequence for the Green's function, then at temperatures of order 1 over n, you do find violation of breakdown of scaling or times of order n over u. Okay, and so this is then a property both of the black hole solution and of this property of this theory of the SY complex SYK model, and that's again one of the correspondences which is so well understood today. Okay, all right, so that's then a review of the complex SYK model, and we're going to now take the lessons we've learned by now understanding well after many years of, it's great to have finally one example of a fully understood non-Fermi liquid is what I would say. So now let's get to the Fermi liquid that we really want to, non-Fermi liquid really want to understand, because it's microscopically much closer to experimental situation. So I'll take a very specific model and just review some basic properties. So you take a Fermi surface in 2 dimensions, where you have some fermion whose energy vanishes on this line, where E of k equal to 0. And I'm just going to take that fermion and couple it to an emergent gauge field. Now, in the real world, of course, the electron is coupled to electromagnetism. And so this is also a theory of an electron coupled to electromagnetism. The only trouble is the electromagnetism is so weakly coupled that the effects of the quantum fluctuation of electromagnetism on the Fermi liquid theory are completely negligible. So even though in principle this could apply to physical electromagnetism, in practice we never worry about such effects. However, if the gauge field is an emergent gauge field, as appears in various theories of correlated electronic states, various spin liquids, states with anion excitations and bulk topological order. There are many examples, and you end up with some emergent gauge field. And also in the Halpern-Landau level, there's the famous Halpern-Lee-Reed theory has a similar, essentially this same effective model. Okay, except there's a Chern-Simons term, which I will not talk about. All right. So here's the theory then. This is the basic theory. I've actually also ignored the time component of the gauge field because that's screened by the Fermi surface. It's a compressible state, and it leads to screening, and there are no long range effects associated with that. So we can just focus on the spatial components of the gauge field in Landau gauge. In fact, del dot A equals 0. And this is our complete theory. You have some electrons or fermions have ignoring spin at some chemical potential mu, some dispersion var epsilon of k, and you couple it with some coupling constant g to some U1 gauge field. So now it turns out this transverse fluctuation in the gauge field do have a very strong effect on the excitations on the Fermi surface, and this has been studied over starting from the mid-early 90s a great deal. And let me just summarize the basic result, but in a language that zooms in really on the very low energy properties right away. So it turns out that the key way to think about it, the most simplest way to think about it, is to use what's called a patch theory. So you just pick 2 points on the Fermi surface. It doesn't matter which 2 points, because in fact the theory has a sliding symmetry, and but I won't get into those details. So we just pick 2 points and 2 antipolar points, k0 and minus k0, and you choose axes this way, and you look at fluctuations of fermions near this point and that point. Now the gauge field comes by, and let's imagine the gauge field has momentum q. So that gauge field is going to scatter the fermion. And so now we notice one thing: when the wave vector of the gauge field is parallel to y, tangent to the Fermi surface at this point, then it'll be scattering fermions whose energy doesn't change at all because you're tangent to the Fermi surface. So that's, you expect to be the most singular process. So a gauge field with q along this direction naturally then couples most strongly to fermions at these 2 points. If it had a different q, it'll couple to other points. All right, so we focus on these 2 points, and therefore our gauge field naturally will have a wave vector q along this direction. And so that also means if we're looking in Landau gauge where del dot A is 0, the only component of the gauge field we need to worry about is the one along the x direction. So that's why you take this and put A as 0. So now I just do a gradient expansion about this point for this particular gauge field. And this is the theory that you get. So this fermion has it's a chiral fermion, which is right moving in the x direction here and left moving at this point over here. So that corresponds to this having opposite signs, I by dx. And it has a quadratic dispersion in the other direction, and you need to keep that. That's one of the key things. Sometimes people think of Fermi surface as made up of one-dimensional fermions at every point in the Fermi surface. There's many papers doing that. That's totally inadequate for this problem. In fact, you do need to worry about the fact that the Fermi surface is not flat, that it has a curvature. And that controls the IR theory. Okay, so this is just the minimal coupling then, and there's your A. Okay, this is the Maxwell term. And that's it. So that's the basic theory on which we've been worrying about a great deal. And really there is no firm answer on what the properties of this theory are. Well, I think we're pretty confident we know what the answer is, but there's no proof at the level that we understand the SYK model, for example. So, okay, but what are so let me just give a simple argument of one of the basic results, which can be obtained by many different methods. Let's imagine that this theory, and I do perturbation theory in G, flows to some strong coupling fixed point at some high value of G. So I just want to understand what is the structure of the fixed point. So if I imagine that there's some scale invariance and I'm going to scale X and Y, well, clearly because of these 2 derivatives, I want to scale X and Y with different powers of S, which determined by differ by a factor of 2. And you can prove actually that factor of 2 cannot be renormalized because of certain symmetry of the theory. then time can scale with some exponent z. So that's the dynamic critical exponent. And we will find that the correct value of z is actually bigger than 1. And that means that, in fact, this d by d tau term is just disappears. It's irrelevant. We're going to assume that the bare term disappears. But that should sound very familiar because that's exactly what happens in the SYK model. This term doesn't matter. And that's what's going to happen here too. So you just do these scalings and you demand that the action remain invariant. And what you find is that the coupling G scales in this manner. This is just trivial power counting. And then if you assume that G is some fixed point, you have some scale invariant theory where G being dimensionful doesn't matter anymore. Well, you can see from this very simple argument that that's only possible that if Z is 3/2. Okay, so that's the simplest way to get Z equals 3/2. You can do various other explicit computations, which was, I think, first done by Patrick Lee in this context, involving evaluating various two-loop graphs, and that's indeed the answer that you get. Okay. So another curious thing is that once you ignore this term, then you can see actually the symmetry of this Lagrangian is much bigger. You can even do a time reparameterization because there is no time derivative. You can reparameterize time with this function with f of tau, and see that the Lagrangian at least formally looks invariant. So you might wonder, well, maybe there's some reparameterization symmetry here that we have to now worry about. Okay. And if you do explicit computations, this is the general structure of the Green's function that you find. And this is the bare Fermi surface you began with. But the self energy becomes more important than the I omega term, at this omega to the 2/3. And the 2/3 is related to z equals 3/2 because this is linear length, and that's 2/3. So omega scale is k to the 3/2. And this is the kind of singular self energy you get, showing that, in fact, quasi-particles don't exist at this Fermi surface. Okay. Yes.
Maybe a question and a reminder.
Yes.
So the question is, so in this Green's function, what happened to the k-squared?
Oh, that's in here. This is mod k. So if you expand this out, you'll get a kx plus ky squared. The mod k will become a k squared.
But didn't you say that
this is just
one
different.
direction
If you
was
take, if you
k and the other one was k squared?
Okay, this is k being measured about 0 momentum.
Okay.
If you take this quantity here, mod k minus kf, and you expand about k naught, that's exactly kx plus ky squared. Okay, and, it's the same thing.
Yeah, thanks. And the reminder is that, well, you've been in for like half an hour, more or less. So
okay,
I'm not sure how how long you have left, but that's
yeah, all right. I'm almost done. Maybe another 3 minutes, if you don't mind.
Yeah,
3 or 4 minutes.
Yeah,
I had a few questions in between also.
Yeah. Okay.
Subir, can I quickly add to the questions very quickly? Just curious, suppose you integrated out the fermions at this point and derived an effective action for A. I don't know if it's possible, but would you expect anything cool? I mean, if
Oh, well, there's literally a million papers on that. So what happened? The reason there's trouble with that is if you get some effective action of A, I mean, that's really the canonical approach with the factor of n out front, because you can take n species of fermions. But then when you compute the self energy will have a 1/n here. There'll be a 1/n in front of this omega to the 2/3. And that leads to problems because you have to compare this term, which does not have a 1/n, with this term that does have a 1/n. And then there's various higher loop graphs, as pointed out by Sung-Sik Lee, that lead to a breakdown of the 1/n expansion. So the naive 1/n trick of just taking n species of fermions and integrating them out does not work. So that's why there is no systematic theory. And we want to ask many other questions similar to the type of questions that we now understand for the SYK model. We want to understand, what are the finite n fluctuations? We want to understand something about instabilities to pairing and various other things that Igor talked about yesterday. Those are almost certainly present even here. And none of that there is no systematic theory for any of that. Although there's no shortage of papers, which I haven't cited here. Okay. All right, so let me get to the new result then. So it's a very simple trick, and I can, in fact, I hope complete very quickly. This is work by these three people who I've already mentioned. Ilya is a postdoc at Harvard, Hayu is a student at Harvard, and Avishkar, former student, now postdoc at Berkeley. So basically what we're going to do is we take the same theory and we take n flavors of fermions, so index alpha, but the gauge field, which I now represent by a boson, generic boson phi, I'm sorry, this should be a phi here. Oh, well, sorry, I call it A. So this should be A here, sorry. M flavors of boson A sub alpha. And n over m is some fixed number. They're both going to go to infinity. And then I'll take a Yukawa coupling, the G, and make it a 3-index tensor, G alpha beta gamma. But no, and this will be a random number, okay, in the spirit of the SYK model, where G alpha beta gamma is 0, and its variance is G squared. So there's no spatial randomness, and we do expect G to flow to some fixed point. So, you know, whether even if we take some set of numbers, we don't expect to obtain any generically different non-Fermi liquid. So it seems quite reasonable. You take a set of random numbers and you just average over this theory. So you take this theory, you look at the average partition function for these random Yukawa couplings. So that's the basic idea. And as I'm sure many in the audience know, this is an idea that's very much in vogue these days in quantum gravity, where you take averages over conformal field theories. So here we're taking averages over this particular compressible field theory. Okay. All right, so if you take averages, then life becomes simple. Then you get G sigma theory. It's in the large n limit, the average partition function. It has the very basic same structure, very similar structure to the SYK model, but one very important difference. The important difference now is that these fields are not bilocal just in time, but bilocal in space-time. So capital X is a 3-dimensional coordinate. So this is really a bilocal theory in all of space-time. So this is an even bigger path integral. But of course, the beautiful thing is that the factor of n here that you can get up front. You could not, no one knows how to do that for the original problem. But once you average over theories, you can do it in a few lines. All right, so now the saddle point equations are in fact these equations, which can be solved exactly, even with the k dependence, and the exact solution is very similar to the SYK solution. In fact, the self-energy of the fermion turns out to be independent of momentum k. We have the same 2/3 power that I gave you earlier, and this is a scaling function, which is not the simple Fourier transform of the sine function. It's a more complicated function, but it has the same feature that there's no microscopic energy scale, and it's a function of omega over t. And that this is the exact solution of the saddle point of that average theory. So starting with the saddle point, and now we can do many things. So I'll just summarize. I refer you to a paper for more details. You can look at, we can basically now turn the crank from everything we learned in the SYK model and apply it to this bilocal theory. So the first thing you look for is that, is there this time reparameterization soft mode and associated violation of scaling when your frequencies becomes of order 1 over n? And the answer here, in fact, is no. At least we couldn't find any. There is, in fact, no zero mode that's connected to time reparameterization. And this has to do with the fact that there's a non-trivial action of the seeming time reparameterization of the spatial coordinates. And the spatial coordinates do matter. And there isn't this, there is also no bilocal structure in the Green's function once you include the spatial coordinate, the saddle point Green's function. So in fact, this turns out to be not important, and we can really show that. The only low energy modes in this time reparameterizations are basically the density and the energy. and they have well understood spectral properties, which don't need you to worry about any singular effects coming from them. Then we can try to look at 1/n correction to exponents. Well, we haven't done that, but at least now we can say which graphs need to be looked at. And they're complicated to this kind of self-consistent theory. I should say, you could do this to, what's called Eliashberg theory in condensed matter. It's, there's literally, again, a million papers in Eliashberg theory, which is, in the end, really, again, a somewhat uncontrolled theory, especially when you're looking at critical points. And this could be applied to any of those theories. And there's been no understanding of what are corrections to Eliashberg theory. So this is, in fact, the correction. We believe the most important corrections. There's a bunch of graphs that you have to write down in terms of these bilocal fields. And you can see it has some flavor of a string theory here. This is what it looks like in the bilocal fields. If you want to see this is the same graph, but in terms of the original electrons in the bosons. And these are the two graphs that appear out of 1/n, and these could lead to corrections to Z, but no one's computed any as far as we know. And finally, we can look at the analog of the problem that Igor talked about, again, very systematically. The coupling G that drops out completely. There are operators of Cooper pair and charge density wave operators. They have complex scaling dimension. They could have real scaling dimensions, which are universal that you can compute. And they could have complex scaling dimensions implying instability to superconductivity and various other interesting phenomena. So thank you very much.
Thank you, Subir, for this very interesting talk. Are there any questions? I think there's Elias.
Hi, Subir. Thank you for the talk. From what once remember, somebody explained to be Eliashberg theory, and what I understood is that this is taking these Wigner-Dyson equations over theory, truncating them and solving them. Now, in principle, for any theory, you can write down these Wigner-Dyson equations, and then you can try to make approximations. What is the approximation in your case?
Okay, so this is an example of an Eliashberg theory. Like you said, you have some self-energy. In this case, you have a fermion and a boson, so you have two self-energies, sigma and pi. And then you have some simple result, expression anyway, for the self-energy in terms of the exact Green's functions. So self-energy, just like in the SYK model. So self-energy is some power in real space in this case of the exact Green's function D and G, both self-energy. So that's what I would call Eliashberg theory, where self-energy is some simple expression in terms of the exact Green's function, period. So that's Eliashberg. Now, once you have these equations, now you want to solve these equations. That's not easy. These are, you could put on a computer and various people solve them, and they make various approximations to solve them. Here, my claim is that at least at low energies in the scaling limit, there is no approximation. You can just solve these equations and get this exact result for the self-energy in the scaling limit. So that's point number one. The other point is, of course, these are approximate equations to the real problem, even in this case. Question is, is there some systematic way of correcting them? And I believe there hasn't been any clear-cut answer to that question. And what we're proposing here is that if you take this average theory, which is I think, very reasonable when you're near a critical point. If you're, if you're really want numbers which are microscopic for a given system of your interest, then you wouldn't want to do that. But if you're interested in these universal critical properties, I think this is a very, very natural thing to do. And so you take the average theory, and then in the average theory, we finally have a parameter, which is 1/n, which at least formally can allow us to look at corrections to Eliashberg theory. They're not very simple. They're given by horrible graphs like this, but we can systematically list them anyway.
Okay, thank you.
I think Grisha is next.
I have a question. So in this Schwinger-Dyson equations you showed, so the self-energy and polarization operators, they they don't depend on space, right? At the end, is it? They both the p and
no, pi does depend on space. It has a 1/k dependence on space, but sigma doesn't. Yeah,
I see.
Pi does. Pi does. Yeah. I haven't written it down. It's in our paper. Yeah, I mean, it's been known. So the fact that this is an exact solution, I think probably was Polchinski had a paper where he made this point long ago. Essentially, this point that this is an exact solution of these equations. Yeah.
And the other question is, so for this 1/n corrections, these diagrams, are they the same as an SYK model, or there's some difference?
They're very similar. I mean, of course, you have to, in SYK model, you have a G and a sigma. Here we have a G and a D, and a pi and a whatever I called it. So you take the SYK model and make everything a matrix. The Green's function themselves become matrices in the fermion boson space. And then it's, in that abstract sense, they're the same graphs. Yeah. So, in fact, these type of graphs appear in the Kitaev-Silp's paper. They call it sheet and seam corrections. So they're, but there's many more indices. So there's momenta, there's extra indices. So it's much more complicated than SYK. But if you take an index-free notation, then they're the same.
So like for like a free energy, the leading 1/n graph would be just a donut with a ladder, right? So
I think so. That's correct.
Yes. Okay. Right. Thank you.
Max, I think you have a question.
Hi, Max.
A couple of quick questions.
You're muted. Oh, go ahead. Yeah, now you're fine.
The boson, the pi, is it of Landau damped form?
Yes, of course. Yeah, that's what comes out from this equation.
I see.
It's a small omega over q. Yeah, I mean, I'm not. These are things you know extremely well. Yeah, there's nothing new here really. I'm just presenting it in a somewhere. I mean, at least this page. This is all.
But there is no
maybe the scaling.
There is no 1/n in front of sigma.
That's the key point. Exactly. So when you take the random theory, there's no 1/n here. That's the big difference from the previous approach.
I see. But the sigma equation is not the same. That
equation. No, it's the same. The saddle point equations are the saddle point equation of this average theory are essentially the RPA equation. They're no different. The self-consistent RPA Rashberg equations for this problem. But there's no 1/n, and they are. Once you average over these couplings, then you get an n out front of the action without getting it in front of the self-energy. That's, seemingly it's at this level, it's a formal trick, but then it gives you a lot of insight on how to look at things beyond the RPA, like pairing instabilities, CDW instabilities, time reprogrammizations, corrections to exponents. All are systematic at this point.
And Subir, maybe you could say a few more words about these instabilities.
Yeah, so you have to sum these ladder diagrams just like in SYK, and you have to look at the eigenvalues of the kernel of the ladder diagrams. You have to do this in K and omega space for the particle hole sector. It turns out, so here I'm referring to this last part here. For the Cooper pair sector, in fact, the equations in the end become identical to the equations that Igor and Grisha have studied for the SYK model, the coupled XYK model, because the Q integrals can be done exactly because they're all orthogonal to the Fermi surface. And so you get essentially the same equations you got for the SYK model for the Cooper pair scaling dimension by summing these ladder diagrams. For the CDW, it's different. CDW, we get integral equations that are more complicated than you get for the SYK model, but you have to solve them numerically, but they have, again, the same features. So you find some scaling dimensions for the CDW operators. Sometimes it can be complex and tells you that there is a CDW instability, and sometimes there isn't. So it's all And they're all universal, they're independent of the value of G, only depend on this ratio of M over N, essentially.
I see. So are there cases where there are no instabilities?
Yes, there are. Yeah, there are a few cases. I don't remember the detail. Actually, no, sorry, I've misspoken here. They're not entirely universal. There is this, when you have two different bosons, and there is a bare diamagnetic susceptibility that comes in. Sorry, I should correct that. That's correct in our paper. There is another free parameter in there. Yeah.
But it's
when
all
you have more than one boson.
But it's all in this two-patch theory. There is like no inter-patch coupling that becomes important. Is that right?
No, yeah, no, it's in the two-patch theory. It's all in the two-patch.
Thank you.
Okay.
Can I ask one more question?
Yeah, please.
Yes, please.
That's a question to the first page, so the very, very general stuff of Subir in the beginning. Now, you mentioned what is not a compressible fluid, but do I understand correctly that compressibility in this case meaning that you have charged gapless excitations?
Absolutely. If you have a gap system, cannot be compressible.
Okay, thank you.
For the simple reason that since Q commutes with H, if you add a very small term, when you're not changing the eigenfunctions, you're only changing the eigenvalues. So basically, if you have a very infinitesimal correction to the Hamiltonian, every eigenvalue is changing a little bit, but the eigenfunctions are the same. So if you have a gap, then the ground state remains the ground state. So the charge doesn't change. So a compressible system must be gapless, that's for sure. But not all gapless systems are compressible because they are like Dirac fermions. They're not compressible above 2 dimensions, in two and higher dimensions.
Thank you.